In search of the perfect Vario. Ever since gliders first flew in thermals, we've been searching for better variometer sensing systems and better variometer presentations to help us understand what the air around us is doing as we're flying. In Search of the Perfect Vario is a re-recording of the talk I gave at the SSA convention in 2023, Reno. This is a survey and overview of techniques, theory and approaches, commercial products, and research projects. And I'll try and minimize the math in public. While the total energy discussion focuses on high performance, high cruise speed, modern gliders, most of the talk is applicable to all gliders. In this talk, I'm going to reference a number of papers and links and information about how to obtain these is in the slides, which are available on my website, www.nadler.com. I'm Dave Nadler. May 2023 is the 50th anniversary of my first commercial engineering job. I've been gliding almost as long, and I bought my first glider 46 years ago. Many of you know me as the designer of the ILEC SN10 flight computer and variometer system, as one of the team that created the PowerFLARM anti-collision system, for my work bringing FLARM to the United States, and from flying contests together. Also, I serve on the OSTIV sailplane development panel, where I hope to help improve the safety and reliability of motor gliders. If you're not already an OSTIV member, I'd strongly encourage you to join. There's a lot of very interesting research that gets published in the OSTIV Technical Soaring Journal and certainly presented at the OSTIV conference. So join, and you'll find a lot of interesting material, some of which is referenced in this lecture. In Search of the Perfect Vario. I'll start by discussing what we really want from a variometer, which is not at all as obvious as one might think. To explain what a variometer sees, we'll talk about thermal structures and gusts from both recent theory and recent measurements. We're going to also discuss why TE sucks, TE suction, the inherent difficulties with total energy variometer implementations, and proceed on to a bit about sensors leading up to inertial varios and commercial products and research projects in inertial variometry. And finally, I'll say a few words about what's possible in the future. This talk reflects my best understanding of what we know, and if I've missed anything or got anything wrong, please let me know. One final note, these topics are all completely intertwined, so there's no start and end point. I'll try to minimize the forward references, but please bear with me. First, thanks to Clemens for providing me this video clip. When you're watching this clip, I want you to look carefully at the variometer needle and listen to the audio. And watch what happens. Enough of that. You can see the needle is swinging wildly. It's bouncing off the pegs. The audio is all over the place, and neither of these are any kind of sensible proportion to or phase to what the glider is actually doing. Many of you have seen this kind of variometer behavior in a glider, and really, if you have a system like this, you should just throw it out. Or at very least, you need to turn off the audio while you're circling. It's really not helpful. It's tiring, it's distracting, it's annoying, and it's utterly counterproductive. Okay, so what do we want? We can see that we have a lot of room for improvement in the climb from the video that we just looked at, but the biggest need for improvement in variometers is actually during cruise. Whether or not to stop is the most important decision. Should I turn right or left, or proceed straight, and mostly avoid turning where there's no thermal. Avoid at all costs turning in foolers. We also need to know if there's a gust field without lift. If you're into team flying, you've heard the term bubbling. And bubbling means there's activity but not lift. There's thermal convective activity in the vicinity. I haven't found a thermal yet, but it's time to be paying attention. I'd like to know where's the best lift, and we'd like to know, if not where's the best lift, certainly where's reduced sink. And that's certainly possible with remote sensing vehicle-to-vehicle communications. Bob Salvo in the 80s in New England built a system where a couple of gliders could fly a few wingspans apart and get indications as to whether to turn right or left, depending on which glider was going up or down most advantageously. We very, very much need wind measurement that works. Everybody thinks about wind measurement as needed for final glide, but it's also very, very important to find lift streets and sink streets and avoid flying in sink streets. And it's also a prerequisite. A good wind measurement is a prerequisite for a lot of the calculations and variometry we're going to talk about later. So I'm going to spend a bunch of time on wind algorithms in a little bit. But wind is incredibly important for many reasons. You got to have it for efficient cruise to stay out of sink streets, and a prerequisite for what we're going to talk about. What we do not want in a variometer is, first and foremost, a long delay before an indication, as with the current TE systems, where we're typically flying with something like a 3-second time constant, and that means you're in the next county by the time you get an indication. We do not want lots of indicators bouncing around wildly, needles or audio, as we saw in the video clip. We don't want false indications from gusts. We don't want gusts being shown as lift and fooling us into making a turn. But the gust indication is only one problem. There's a lot of other things that can cause false indications. So pulling and pushing, moving the flap handle in a lot of gliders can cause big variometer excursions where there's no, we just don't want that kind of indication. We don't want uninstallable or unaffordable instrumentation. We're going to spend a few minutes on that later. And most important of all is we don't want instrumentation that increases the amount of time we're heads down. We need to be spending our time looking outside, understanding what's going on around us. It's not just safety, it's also you're going to go faster if you spend more time looking outside. Now let's talk a little bit about what really goes on in thermals, what thermals really do. So first off, why does air rise in a thermal? Everybody always says, because the air's hotter. Well, not necessarily. That's not necessarily correct. The air rises in a thermal because it's more buoyant. And it's more buoyant, not just because it's hotter, but because it's more moist. So we've long known that moisture can help lift. We have a lot of special situations that where moisture directly causes lift. So in New England, we have beaver ponds. And in Australia, you have small irrigation ponds that are part of irrigation canal systems. In Florida, you have various special effects from lakes. And these are areas where you have a lot of heat collected and it pumps a lot of moisture into the air. So in these situations, you can have reliable lift at low altitude caused primarily by moisture. So, in fact, moisture is more generally a major contributor to lift, and I forget who coined the term, but it's been suggested we should call them moistals and not thermals. A couple of German guys put a temperature and humidity probe in the nose of their Ventus and did a bunch of thermal transits where they flew across thermals measuring the temperature and the humidity. And they showed that they found no difference in temperature going across the thermal, but they did find increased humidity. And that was in 90 hours of German soaring conditions. You can read a very nice paper they published in OSTIV Technical Soaring. It's volume 45, number 1, January to March 2021. There's a lot of horizontal flow in thermals, and various literature says up to 15 or 20% of vertical, but that's maybe not enough. Very basically, thermals are wider at the top than at the bottom, and that means that there has to be a horizontal component in order for them to grow outwards as they rise. When you approach a thermal, you're typically going to see a gust, not always, and you're typically going to see it from the front. So if you approach directly towards the center of the thermal, you're going to see the gust head on. If you approach the thermal to one side, as in this case, the gust is going to be from the side, and it's actually going to deflect the yaw string a little bit in the direction away from the center of the thermal. When you approach a ridge, a thermal on a ridge low, the gust is actually in back of you, which is why you have to keep your speed way up when you're low. So this phenomenon is discussed in various places. So Tom Knopf had done this in some briefings, which I don't think he published. More recently, Kevin Atkinson has published what he calls string theory, and that's been discussed in British Sailplane and Gliding, and also in the British Gliding Association's 2015 Advanced Gliding Training Notes. In the last slide, I discussed how Oliver Perdelli and Ronald Niederhagen measured no temperature difference in their transits of thermals, only increased humidity. Showing how moisture drives thermals with better modeling of moist air convection is an important contribution from Oliver Moss, for which he won the 2021 Summer OSTIV Conference's Best Presentation Award. So let's have a look at Oliver's large eddy simulation of moist thermal convection without cloud, and this is for relatively weak thermals. In the simulation, the color denotes temperature, so blue for cold, red for hot, and the arrows show the direction and magnitude of the flow. So here you've got strong vertical flow, here you've got flow that's slightly off, it's got a slight horizontal component, here you've got purely horizontal flow. So as we look at the video, a couple important things to note. So first of all, we're going to see the core of the thermal can be colder than the surrounding air. Horizontal motion is pretty big, and that is what we interpret as gusts. And you see a 45-degree arrow, that's 70% of the same size of the vertical arrow, then you've got pretty big horizontal component. And the other thing to note is that the circulation occurs outside of thermals in residual vortices. So let's have a look at the simulation now. So here you can see hot air rising, but colder at the top. And then some other instances you see that the air that's rising is pretty cold. So near the bottom of the plume, it's hot in some cases, but in a lot of cases you have strong rising air with it's not hotter than the surrounding air. And in other cases you have very weak temperature differences, but here you can see it's even colder than the surrounding air. And also you can see the very strong horizontal motion, gusts out of the thermal here, into the thermal at lower altitudes, and that will derange the Vario as we will see. The total energy variometer was invented sometime before 1940 in the United States by Arthur Kantrowitz. He was using a Venturi. I don't know what year he actually invented it, but he published it in 1940 anyway. And of course, this has been successively refined by Dieter Althaus, Orrin Nix, Rudy Brotzel, and many others. And the principle of the Venturi or the TE probe is the same. The suction generated by airspeed at the Venturi or the back side of the TE probe is equivalent to the reduced pressure that would be generated if you just took the glider and raised it corresponding and changed the potential energy corresponding to the current kinetic energy. So this worked great in older gliders, but you can see that the true airspeed squared term is a bit problematic, because the faster we're going, the bigger any error is going to be. And as we start seeing horizontal gusts, as we looked at in the previous slides, you can see this is going to cause successively some bigger problems with faster gliders. So you've all probably seen this slide before, since I first presented it at, I think, the 1996 SSA convention, and shared it with many other presenters who used it. But you can see that a relatively small horizontal gust creates a very, very, very big reading as you go faster and faster. And some of you are going to say, well, you know, these look like crazy cruise speeds. But remember, this is true airspeed. And 110 knots cruise is pretty fast, but that's 150 knots. 110 indicated is 150 true if you're flying a cloud base at Nephi or someplace like this. So this is maybe not as important for a 126, but for modern gliders, it's a really, really big problem. So what do we do? Well, everybody slows the variometer down to avoid the indication pegging. And we're typically flying with time constants up to something on the order of 3 seconds. And that means that the indicated variometer, whether it's audio or on the needle, is too slow for making decisions. So really, the reality is that all experienced pilots sense and react to thermals before the Vario indicates anything useful. And we use the variometer just for confirmation of what we felt. So we feel the thermal, we hear the different sound the glider makes on encountering the thermal, and that's what we are really doing. And if you don't believe me, go turn all your variometers off and go fly a 300K, and you'll find it's really not that hard. It's a bit more difficult on days with lots of gusts, lots of foolers, as we say, but it's not that hard. And many of us practice with variometers turned off to get better in tune with what the glider is telling us. So this problem is true whether we're using a TE by probe or TE calculate, because the airspeed sees the same. I mean, the reason that we see the big effect is from the airspeed component, the true speed, and it doesn't matter whether you're measuring it from pitot or the suction of the TE probe. It's the same issue. And you should also recognize that with the true speed squared term here, any errors in the pitot-static system or the sensors can aggravate the gust sensitivity. And I'm going to do something I promise not to do any math in public, but suppose we transit a 1 knot gust at 50 knots or 100 knots. And we look at the V squared term. Well, the difference is just 51 squared minus 50 squared is 101, or 101 squared minus 100 squared is 201. Okay, so you see a factor of 2. Well, why did I say it's a factor of 4? In other words, the square of the increase in speed. Well, the reason is that as we double the speed here from 50 to 100, we have the time that it takes to transit the gust. The variometer senses energy per unit time, so if we double the speed in half the time, and we see twice the energy, the squared term, well, we're going to see 4 times the Vario indication. So again, it's the square of the ratio of speeds. Double the speed, 4 times the indication from the gust. I don't know of any publications of measured or theoretical convective gust characteristics. If anybody knows of any such articles, please drop me an email. But let's take a look at some gust characteristics from both theory and measurement that I've been able to gather here. First, Oliver was kind enough to make this plot. And what he did here was he sampled a horizontal path through the simulated flow and plotted the vertical and horizontal components of air motion. So you can note that the peak horizontal flow is the same order of magnitude as vertical, not quite as big. And remember, he's modeling weak convection. In this graph, you can see the horizontal axis is in kilometers, meters, and each gradation would take about 30 seconds to transit at typical weak thermal cruise speeds. So what we can see here is that often, but not always, a gust precedes a thermal indication. So here you have the horizontal gust in red. 5 seconds or so, or 10 seconds later, you have the actual thermal. Here you have the gust, and sometime later, the thermal. Here you have the gust, and sometime later, the thermal. Not always, but As you can see, it's often the case. So that's theory, but what about actual measurements? So Patrick Grady in the USA built an inertial variometer, which we're going to talk about in a little bit. And as part of this development project, the way we do all these things, we do a lot of data logging. And Patrick logged the data from his Vario sensors and output, along with the output of an ILEC TE Vario. And Patrick was kind enough to put together this plot, which compares the inertial variometer to the ILEC and derives the gust velocity. And again, you can see that very often the gust, which is in whatever that is, kind of a light blue, precedes the Vario indication. And you can also see that the gust, in many cases, causes the ILEC to produce a Vario indication. Vario indication from the ILEC is in blue. So you can see the gust, the ILEC indication, but the red, which is the inertial Vario, isn't perturbed by the gust. Here again, you can see some gusts, some indications on the ILEC Vario, with less indication on the inertial Vario, and then finally here you get gust followed by the real thermal here, and that you can see is typical here. So you can see here the gust, the ILEC indication, and then when we get to the real thermal, we see the inertial Vario. That pattern is, you can see, repeated here a few times. There's some errors in the gust measurement here, and I think, or inconsistencies, I should say, and I think that has to do with difficulties in Patrick's wind model, which we're going to talk about in a bit. But again, to summarize here, you can see that both theory and measurements show us that horizontal gusts are quite significant. And thanks again to Oliver and Patrick for preparing these plots. So what are we going to do about TE measurement? We really do want to know about total energy changes, but we really don't want gusts included in the presentation that we see for lift. We want a separate presentation to alert us to the fact that we're in a gust build, but we do not want a Vario indication showing an increase in energy when that's not really what's happening. So a perfect Vario has got to identify gust versus lift signals. And again, the gusts are not noise. We do want to know about them, but we do not want them indicated as lift. So when we look at the signal measured by a tail probe, well, any total energy and pedostatic system, you see the apparent airspeed jump from the gusts. We may see it for a tail-mounted probe, effects due to the G load changing on the vertical column over here in the tail, which changes with pitch and bank. We're going to see flow field changes inducing pedostatic changes when we change our flap setting, when we change our angle of attack, pitch changes. All this stuff impacts the signal that we're going to see at the probe. We are going to see delays from when the signal hits the probe to when it shows up after 20 feet of tubing up in the if you've got the electronics and computes up in the instrument panel. And of course, on top of this, any measurement system errors compound the difficulties, and that could be difficulties with the pneumatic input or difficulties with the actual sensors. So to summarize, the next generation variometer has to decompose all this information, and there's actually some more, and clearly present lift, gusts, and wind without making it confusing to the pilot. Accurate wind measurement is required for advanced variometers that we're going to talk about. I'm going to spend a couple of slides on wind measurement. So the most simple case is you have a GPS track, which is a vector, actual track over the ground. You have the glider's motion through the air mass, and the vector difference is just the wind. The track through the air mass requires the true airspeed and the heading. And so that has a couple of interesting issues. So first of all, you've got to have good true airspeed. That means you need a good airspeed sensor, which a lot of instruments don't have. You have to have a decent pedostatic system or a compensation system, and you need an altimeter and accurate outside air temperature. Otherwise, you can't compute density altitude, and you need to have the density altitude you get from your indicated airspeed to your true airspeed. The other problem is the compass heading, really. That's going to be either a magnetic compass or a GPS compass, which we'll discuss a little bit in the next slide. But if you don't have good true airspeed and you don't have a good heading indication, you can't really compute the wind, at least not directly. So, again, we need this for reasons we're going to talk about later. Can you do wind measurement without a heading input? And why would you want to do that? Well, the reason we want to do that is because the heading sensors are really quite problematic. Magnetic compasses are hard to install, so they work. In the glider, you have lots of welded components, and the Earth's magnetic field is really tiny. So these welded components are not degaussed. They have their own magnetic fields. You have the magnetic field lines are distorted by any steel components in the aircraft. So there's a lot of issues with the magnetic field itself, never mind the sensors. So it's hard to install them so that they actually work. GPS heading is an alternative. A GPS heading system is a special kind of receiver which has two antennas, and it looks at the differential position between the two antennas. And this is not just two cheap GPS receivers. This is a special GPS receiver to do this properly. It's a bit expensive and it's a bit difficult to install. If you orient the two antennas along the fuselage axis, you get heading and also pitch. In 2006, GPS heading sensor I used cost about $5,000, and the one I'm fooling with now is around $600 with the antennas. That translates into something like a $2,500 retail price for a consumer glider instrument, and add to that the installation cost. So neither of these are pleasant options. But fortunately, a heading sensor isn't required. So let's talk about that a little bit. Without the heading, if you have good indicated airspeed, true airspeed, you really need that, but you don't know the direction, could be anywhere on a circle. The vector could be anywhere on a circle. If it, for example, your actual heading through the air mass is this way, then the difference with the GPS track gives you this wind. If you're heading through the air mass is in this direction, the difference with the GPS track gives you this wind. So you can't get directly the solution from a single observation, but you can get a solution using multiple observations. It's an interesting algorithm. It's numerically a bit difficult. You've got to consider, if you're going to try and implement this, what happens with multiple similar observations. And also the noise is pretty high. The GPS track is a derivative of the position, and that means it's even noisier than the GPS position. So there's a lot of noise in the GPS track information, and you have other numerical difficulties. The ILEC SN10 wind algorithm we delivered to customers in 1998, which is astonishingly 25 years ago. So anybody that tells you this is a new and novel way to calculate the wind, please give them a dope slap for me. In the SN10 implementation, if you have wind over 10 knots, you will typically have a reasonable, accurate wind indication from the instrument by the time you're off tow. And I used to worry about the accuracy of this algorithm. We developed it using data sets that we recorded with what we best could estimate the actual wind was from meteorological data. But nonetheless, it was always a worry of how accurate it really was. So in 2006, in the Hobbs Nationals, 18-meter Nationals, I installed a GPS compass and checked the accuracy of this system, and the result was that the ILEC SN10 algorithm was within a few degrees in 1 knot in almost all instances. So it was accurate enough that I decided I shouldn't really spend any more time on it at that point. But there are a few issues. While it's much more accurate than a circling only estimate, There's a bunch of ways you can do it. You can do it with trying to look at drift, centroid drift in a thermal and things like that, but it's typically a lot less accurate than the way we did it in the SN10. One of the problems you have with this is without the heading sensor, if you make a long, straight final glide, well, you don't have any information. I mean, all the observations that you're making are identical, so you have nothing to solve the wind. So the estimate certainty degrades significantly if you make long, straight glides or long, straight flights on a ridge. And this is equally a problem for advanced variometer systems. If you don't have a heading system, again, the wind estimate will degrade over long, straight glides, and then anything you are using the wind estimate for, including gust estimation, as we'll see, will degrade. I'm going to spend the next couple of slides talking about filters, some of the techniques that we use. Apologies to those of you in the audience that are already familiar with these techniques, but just to make it a little bit more accessible to everybody else. So what is a filter anyway? You've seen the old big bottles that are used in gliders for removing quote-unquote noise. What they really do is they filter out a high-frequency component. A filter is just a way of removing unwanted frequencies from a signal, or attenuating them anyway. That's all very well and fine, but gusts do have a high-frequency component, as we saw the measurements and simulated data that we looked at earlier. There's a fairly quick rise time on the gust signal, but that isn't the whole story. You can use a two-pole filter. It helps somewhat. In the old days, Rudy Brodesell built an analog two-pole filter for some of the early ILEC instrumentation. I coded a two-pole filter digitally for my old SN10. But the problem is that the gust signal is large and it's long. So you can't eliminate the effect of the gust. The gust is still going to cause significant variometer indications, even with a good two-pole filter, and helpful, but it delays the signal considerably, the indication that you see as the pilot, and it does not remove the big indication. So that's one kind of filter that we talk about. What's a Kalman filter? The extended Kalman filter first flew on Apollo 11. That's the navigation system. And so, yes, some say it's rocket science, but it's simply, the concept is pretty simple. So let's talk about that a little bit. In gliding, the reason that we care about this stuff is we're going to use Kalman filters to implement inertial navigation systems, and inertial navigation systems to implement advanced variometry. So bear with me for a second. Everybody's seen the equation. And I can't tell you the number of textbooks I've thrown across the room when I encounter that word. But again, conceptually, it's pretty simple. It's a model of a system. It takes noisy, imprecise inputs over time, and at each time step makes a new estimate. And the estimation process is shown here. So X is the system state. X sub P is the predicted system state given the previous state of the system. And to that we add the Kalman gain times the difference between the actual sensor inputs and the predicted sensor inputs. Well, what does that all mean? Let's take a very simple, excuse the oversimplification, of a GPS. So if you consider a GPS to produce a position and a velocity vector, then the next position, the next system state, would be expected, in the absence of any other data, to be the previous position plus the velocity vector times the time difference at the time step. So that's the next projected or predicted state. We're going to add to that the Kalman gain times the difference between the actual sensor inputs and the predicted sensor inputs. Well, if you have no confidence in the sensor input, the Kalman gain is going to be 0, or very small a number, and you're just going to see the GPS march along through space in a straight line at a constant velocity. And in fact, if you cover up the antenna on a IGC data logger while you're driving, you will be able to see this behavior. Cover it up, stop the car, make a right turn, and you'll see, and then uncover the antenna, and you'll see some interesting results for certainly some IGC data loggers. The Kalman gain is where the magic happens, because to estimate the new system state, we're going to use the certainty of the previous state and the certainty of the inputs. Give you some examples of how we might weight or be more or less certain about the inputs that we receive. In a GPS receiver, if we're trying to estimate the altitude that we're at, we're going to have a lot better results with a satellite that's directly overhead. If we're trying to estimate the position, we're going to have a lot better results with satellites that are out on the horizon, because GPS works by distance measurement. So one hopes that you can take the certainty, calculate the certainty of the various inputs, and use that to weight the result. If you have wild inputs, you would hope that, wildly different than what you expect, you would hope that the system would then be able to reduce the weighting of those new inputs. An early GPS system I had showed my position over the North Atlantic while I was soaring in Montana, and that's something that we strive to not have happen with decent Kalman filters. Math is, again, daunting. If you look at some of the notations, the mathematical symbols have more hats than the Windsors. It makes one's head hurt. But basically all we're doing is we're trying to say, okay, let's find the least squared error of the expected result. And we do this just like we do a polynomial curve fit, which is we take the derivative of the expected error, set it to 0 to find a minimum, and solve for the result. So again, we're incorporating the certainty of the inputs, and we're incorporating the certainty of the current state estimate. The system model is only an approximation of the real world, and the results you get with a Kalman filter are going to be pretty variable depending on how well it correlates with the real world. If we think about implementing an inertial navigation system for a glider, and you use the simplistic GPS model I introduced at the beginning of the slide, it's not going to work very well, because it's assuming that you're normally just going to proceed in a straight line. Well, gliders tend to sit in a circle, in a thermal. If your model doesn't incorporate that, you're going to have pretty poor results. And this was found out very early on in the guys that developed the INS for the butterfly found that out, and it's in the paper. That's you can find a reference to the paper in my the online slides. Next, we're going to talk about how inertial navigation systems, inertial platforms, can help create better wind measurement and our variometers. Several research projects and a number of commercial products that have been introduced already are using inertial navigation systems and or inertial measurement units, which are not exactly the same thing, but close enough for the purpose of this talk. How do we do that? Let's start with considering what happens if you have no wind, and suppose you had a GPS that had no errors, no noise, real fast, perfectly accurate. Well, in the case of no wind, you would directly understand your energy situation, because you could see the velocity between fixes, and you could see the potential energy from altitude. From that, you could derive a total energy vario, and you'd have the perfect vario. So what's wrong with that picture? First, GPS is noisy and it has errors. So we need an accurate inertial navigation system for short-term information. Secondly, consider what happens if you're flying at 50 knots true directly into a 50-knot true wind. The inertial navigation system is going to show zero motion, but your kinetic energy is 50 knots because your kinetic energy is with respect to the air mass that you're flying through. That means that you need accurate wind measurement to convert the INS into total energy. That means you need a really accurate wind, because if you don't have accurate wind, you're going to run into problems because you have the same total energy dependent on velocity squared. Your velocity, any velocity error, which is caused by a wind error, is going to cause a variometer reading error. So how do we do this? To my knowledge, the first commercial gliding product using an INS was the butterfly variometer. This was the INS was done by Stefan Lutenegger and Roland Zweigart and supported by Sam Geisinger. And you can find information about where to find their 2012 paper in the slides online. The cell phone revolution has driven up the performance and driven down the cost of MEMS gyros, little chip gyros. So now we have sensors we could only dream about in decades past. But one of the problems with these sensors is they have offset errors and they have a lot of drift. So what we do is we create an inertial navigation system using the Kalman filter. And the Kalman filter takes the short-term information from the MEMS gyro and the long-term GPS information to stabilize and calculate the offsets and drift and remove the drift of the MEMS gyro. So we have a GPS system which is good over the long term, and an inertial navigation system which is the combination of that and the MEMS gyro is good in the short and the long term. So what's the next problem? If we depend on a magnetic compass as part of the input to the Kalman filter for the INS, as we've talked about earlier, you can have a lot of problems with the magnetic compass. But if we omit the magnetic compass, once again, over long, straight final glides, the wind estimate is going to degrade and consequently the Vario calculation. So we have a continuation of the same problem if we don't have a heading system as input. Let's talk a little bit about the sensors that we use to build these systems. In the old days, we had just analog sensors, and these had some advantages. So, for example, the flow sensors that we used to use gave a very nice, big, low noise signal, but they're expensive to produce. We have much better options now with modern integrated devices, and these things contain a complete computer system which does the analog to digital conversion plus calibration, compensation, and provide a nice digital output and operate at higher speeds, resolutions, and better noise. In the case of the analog systems that we used to use, we would have to do our own calibration, and we did this with a controlled temperature chamber, and we would cycle through different temperatures and sweep all the sensors across the pressure ranges and capture the error and then produce calibration curves, which we then had to load into each instrument. So this is expensive. It worked pretty well, but it's not something we'd like to continue doing. So it's a lot nicer to have the integrated digital systems that we have now, but there are, as usual, some issues. First is we have to worry a lot about resolution, accuracy, and noise. As you need information faster, you need higher resolution and lower noise. A Vario needs to detect, say, 50 foot a minute at 18,000 feet. And if you were trying to measure 50 foot a minute over an hour with a really coarse sensor that you could average, you could get by with that. But if you're trying to get a reading every 100 milliseconds, you need pretty fine resolution and pretty low noise. And the analog conditioning that we used to do gave a nice fast result, and faster than some of the early digital output sensors. The earlier digital sensors, in fact, really didn't have enough resolution and had too much noise. And some of the earlier instruments that were based on these low-cost integrated devices consequently had very, very slow variometers. Accuracy can be a big problem, especially for airspeed. Airspeed is difficult because, once again, we're dealing with a v-squared term. So the transducers are spec'd as typically spec'd with a percentage error for the maximum pressure that you're going to need. But that's a really, really high airspeed. And so as you get down into the very low pressures needed for lower airspeed, that same error turns into a pretty big error. The integrated airspeed sensor used in some popular instruments, and we'll talk about that one later, can have like a 5-knot error at 50 knots. And that creates big problems for wind calculation and if you're trying to do electronic total energy. We have now pretty good pressure sensors that we can use for altitude, airspeed, and Vario, but we have to be really careful. A lot of the data sheets are, shall we say, a bit wishful in the characterization of the performance of these devices. I have on my desk here a very nice, beautiful data sheet sensor, and I did a quick and dirty simulated variometer with my PC. This sensor is sitting in a sealed glass jar, and the variometer sits there and wanders up and down between plus or minus 300 foot a minute or something like that. And that's due to the noise. So never mind what the data sheet says. You have to be a little bit careful. When we talk about sensor errors, one of the problems that you have is a lot of the data sheets talk about accuracy, but not really the total error band. And the total error band includes a lot of components that you really need to worry about. You have to worry about the thermal effect on span, hysteresis, and offset, and you have to worry about the offset and full-scale span effects, not just the parameters that are typically included in accuracy. So ensuring that the data sheet really accurately talks about total error band is important. All of the sensors that we use these days, the MEMS pressure and MEMS gyro and magnetic sensor, all have temperature sensitivity. And the MEMS sensors are also sensitive to G and have hysteresis. So the mounting orientation of the sensor can end up impacting the sensor output. When I say sensitive to G, that's what I'm talking about. And again, we have to make sure that we're looking at the total error band and not just the accuracy. One of the more difficult sensors that is in a number of older instruments, and I think it's used in the Open Vario, is this one. Again, you see something over 4 knots error at 50 knots, and this is really going to cause you some trouble for wind. Calibration stuff where we use a temperature-controlled chamber and cycle of pressure is expensive, but one of the other instruments we're going to talk about, it's not just really old instruments like the ILEC SN10. It was also necessary for some of the earlier digital stuff. So the Volter, for example, which we'll talk about in a bit, the Volter Vario did a second set of calibration even on top of the allegedly pre-calibrated digital components that we used, digital output components. What you do is you can include the corrections for sensor error in the common filters, the common model. But that can really crank up the complexity of the model. So you could, for each sensor, for each axis, offset and gain coefficients into the offset amount and gain coefficient into the common model. You could also try to include the temperature effects on offset and gain, but this starts to make the model quite difficult and unwieldy. You can also use the common model to correct for mounting orientation. We know that these things will not be installed exactly upon the axis of the aircraft, and it's best to include the correction for that in the model. Otherwise, customers complain when it doesn't work. Let's talk about some commercial products that are using inertial systems for variometry. And I got to tell you, these are my impressions and based on my conversations with many, many pilots. Certainly not everybody is going to agree with my opinions, but for what it's worth, here's my 2 cents and my best understanding of what's out there. To my knowledge, the Butterfly wind and variometer package is the first system that commercially used an INS for variometry. It was created by Sam Geisiger. Sam was also one of our team that created PowerFLARM back in 2010. Anyway, Butterfly is widely known for a very good wind system and presentation, but while it had the capability to do inertial variometry, it seemed not to work well enough. And many pilots used the regular non-TE, non-INS TE function, and I really don't know why. But perhaps Butterfly's biggest problem was its INS, which we discussed a bit earlier, depended heavily on the compass. and many pilots couldn't get the compass to work. So they had a lot of customer difficulties, and the product was discontinued recently. In 2014, John Warrington in Australia released the Volter variometer, and this was, to my understanding, really the first successful inertial vario. But sadly, the commercial project went off the rails for completely non-technical reasons, and only around a dozen were delivered. The pilots who've flown with it report it works pretty well. In 2019, Mike Borgelt in Australia released the Dynamis product, which has got very good pilot reports, but it's a bit difficult installation. This unit does use a GPS compass, and it requires the second antenna installed on the aft fuselage. So that creates some installation difficulties, and the GPS compass is expensive. It's an expensive product. Mike does not list the price, and he hasn't released any technical information about it, which other than it's not a filter, common or otherwise, which is probably not exactly correct. But anyway, he uses an advanced GPS. My understanding or best guess of what he's doing here is just basically directly, since he's got the GPS heading system, you can directly calculate the wind and counter energy from that. I don't know if he's using an INS other than the fancy GPS, but I hope so, because well, depends on what filtering is going on within the GPS, but you'd like to have the INS, especially if you have GPS dropouts and thermals. In 2020, Benjamin Bachmeier released the Animi. This is a wind-only instrument, no variometer, but it does use an inertial system. And Benjamin Bachmeier also contributed to the LX Hawk, I understand. The website says it's a 14-dimensional nonlinear Kalman filter, which basically, to my understanding, means the Kalman filter includes, well, it means it includes 14 state variables, and presumably that's that model includes then the offset and gain corrections for the gyro, etc. In 2021, we have the LX Hawk, its most recent product, wind and variometer. Sold lots of units through last year. It's got pretty good marks for pilots for function, but not so much for presentation. The Kalman filter uses a model of the glider as well as the wind, and includes angle of attack, interestingly. It doesn't have a heading sensor, and as expected from, as we discussed earlier, I've heard early reports from buddies of mine that it can have problems on long straight glides. That was developed by Heinrich Meyer, who also presented at this SSA convention, and Pen Huang, also Roland Beery, and Benjamin Bachmeier. Home building. Some fun stuff here. We have a long tradition of people building their own glider instruments, so I thought I'd show some fun pictures and then talk about some current research projects. So this is the earliest one I have around. John Firth built his own flight computer for the 1970 World Championships at Wakery, and you can see this uses rather not what we have for components these days. So difficult to manufacture compared to what we have to work with now. I mentioned earlier Bob Salvo in 1985 did the glider differential vario with the communication between gliders to try and steer towards rising air and away from sinking air in gliders routine flying. This is my 1988 suitcase model, as we called it, something like 15 inches long. This was the proof of concept for next generation complete instrument system, which eventually became the ILEC SN10. It was so large that I installed it in my LS6 back then, where my right foot was supposed to be. And I flew this in the 1989 Uvalde 15-meter nationals, and that was a left turn only contest, since I couldn't really use my right foot. Stegøy of Denmark also years ago built his own electronic total energy system, and I believe he used that one in the World Championships. This is a recent project from John Warrington, not a commercial project, just his own project. It's got a Vario built into the probe, and it has a little battery in there that'll run it for 6 or 8 weeks and transmits the results of the variometer to the cockpit over Bluetooth. Probably a lot of research projects I don't know about. Drop me a line if you've heard of something interesting. First, we mentioned earlier Patrick Grady's project. Patrick is a graduate student trying to finish up his PhD at, I believe it's the University of Georgia in Atlanta. This is kind of interesting. If you look here, you can see what he's done is he's using an MTI off-the-shelf gyro. That can create some problems because it has a model which may not include turning, as we discussed with the GPS. He's basically used it's kind of an Arduino style kind of thing, a tiny. He used an RTK GPS, which didn't work well. The MTI IS was what he ended up using, and digital airspeed, total energy, and altimeter. So it worked reasonably well as a Vario in eastern USA conditions and relatively gust insensitive. But he had some challenges, not super accurate airspeed, and especially no outside air temperature. So what he did was he included a correction factor, the airspeed, as a Kalman state variable to correct for density, altitude, and sensor errors, but no offset term. So Patrick assessed that his wind measurements were not great, and my guess is that's probably hurt by the airspeed issue, but also likely because the MTI Kalman filter doesn't account for drift or circling. 2020, this is the Laris team, a group of guys in Germany that formed when they were very disappointed when the butterfly went off the market, and they decided they were going to create their own. This is open source on GitHub if you're interested. There's only a couple flying. They just did the second revision of the sensor box, which is shown here. It also, as you can see, uses the MTI inertial system, as Patrick did, and a conventional single-channel GPS. The interesting thing here is that they believe they've got the compass auto calibration working well enough to deal with the situation in gliders, though that hasn't been tested across a large number of gliders, so we'll see. Also doing a bit of research. Mostly what I want to do first is get a better understanding of what's really going on with the flow around thermals, because I think we're still missing a few bits to really get a perfect variometer. The way we do that is to capture data sets, which we can then use for algorithm development, research, AI training perhaps. This is what I've currently built. So this starts off with a high-quality airspeed system, dual head, dual antenna GPS that'll give me heading and pitch. Temperature and humidity probe is not in the picture. That goes up in the nose of the glider on the multitude of buses this connects to. Absolute pressure transducers for pitot-static and total energy. UPS system so I can not lose data when I have power interruptions, Bluetooth, and an MTI socket that will enable me to use the MTI INS for reference. And people are asking, well, doing this by yourself? Of course not. I've got Rupert to help. What about AI? Can AI be used to get better, faster, and gust-insensitive information out of our sensor inputs? AI is fundamentally about pattern matching, trained from lots of example data. So a typical example you might see is recognizing images of fruit. With lots of pictures of bananas and apples and so forth, you can train a neural network to recognize fruits. But the biggest difficulty is obtaining the training data, which must be labeled with the desired outputs. So you have to have a bunch of pictures of a banana from various different angles, all labeled as banana and not mislabeled. It can take quite a lot of training data and an enormous amount of computing power to generate a neural net. But it's interesting in that you do not need a mathematical model that explains the behavior of the system. Unlike a Kalman filter, where you have to have a really, really good mathematical model, a neural net is quite the opposite. And in fact, when you're finishing training, you don't know how it works. You have a neural net. I mean, you have to select what kind of neural net when you start the process, but you really don't know how the net that you end up with actually performs the pattern matching. So what about gliding? What do we have for training data? To make it clear, we talked a second ago about an example of images, but these techniques can likewise be applied to signals. So taking the inputs, pitot, your total energy, your GPS, and trying to calculate wind and variometry information. We could use visual information. Lots of unmanned aircraft, model aircraft, up to drones, use pictures of the horizon, the camera on the horizon, to stabilize the common filter, the MEMS gyro. We, at the SSA convention, we heard about the Mars helicopter, which uses camera facing the ground to stabilize the IMU, since they don't have GPS on Mars. We could even try to use cameras to recognize cloud development and steer us towards developing thermals. But there you really have a big problem obtaining the training data, and that's probably a ways out in the future. Could you use IGC files? Probably not, because IGC files, the basic IGC file doesn't have a lot of the information that you would need. It doesn't have the sensor inputs like the airspeed. IGC files are extensible. The SN10 IGC files also do contain additional information like airspeed, which has been used over the years to continue to refine various models. But in general, the basic IGC files do not have enough information. Probably impractical to build the models on the fly. We have the information on the fly. If you make a turn in a folder and you don't go up, well, okay, you can label that data right now and then that was a folder. If you had a data log with enough information, you could make that label afterwards. But it's probably not practical, if nothing else, because of the computational load that we'd be looking at. It might be possible to have pre-built models or a few different models that apply to different weather conditions and select the model that most matches the day's weather, but I'm not sure if that's really practical. Anyway, I don't know of anybody that's currently working on using AI to process signals that we have. If anybody knows of anybody doing that, drop me a line. I'd love to talk to them. But I think I started to look at this, but I came to the conclusion that it's probably a better idea to use a common filter approach, because we have a decent shot at a tight mathematical model to be able to accomplish what we need to for better variometry. But AI is definitely one possible way that we could get to better instrumentation. In summary, the instruments we have now are pretty bad. We need to improve measurement systems, especially in the last year or two. Greatly improved sensors have become available at reasonable cost. We need to improve affordability and installation. Requiring perfect installation orientation and perfect magnetic environment for installation doesn't work in the real world. We need especially to improve gust insensitivity of total energy. Gusts need a clear, separate presentation, not just suppression. Presentation in general, especially we need to improve heads down time. It is not okay to have lots of different indicators bouncing around, nor require a lot of heads down time to interpret what the instruments are trying to tell us. That's very, very important for safety, and it's important for our performance, because if we're not looking out the window, we're going to go slower. So in summary, we understand why our instruments are bad, and we see a path forward to improvement, but we still have a lot of work to do. I hope you found this educational and entertaining. And once again, if I've missed anything, got anything wrong, or failed to explain clearly, please let me know. Thanks very much. Questions and answers from the talk. 1. Are you working on a commercial product? Well, I have some ideas about how to make substantial improvements and really make something substantially better than what's out there. Talk is cheap. So what I'm currently trying to do is build a few sensor boxes to collect data, which I'll endeavor to make public, and experiment with some ideas, and we'll see. 2. What does the gust field tell you? The gust field exists because there was or is convective activity in the vicinity. In team flying, we call this bubbling. It should sometimes tell you the direction to a thermal. as discussed above in string theory. 3. Is adaptive filtering applicable? Possibly. I think common filtering is more applicable as we're trying to derive state information not directly present in the input signal, especially wind. If you just try to remove gusts, you might be able to build an adaptive filter that treats the pitot-static input as the sum of real pitot-static plus gust and do some kind of filtering around that. But I'm really not sure if that would work. 4. Can we use simulation data for algorithm development or AI training? Problem is, perhaps our models are not good enough, and it would be unfortunate to do a bunch of training and then find out that the data we use doesn't really match reality. So I think we need more measurement data to see if this really works. The Hawk guys have collected a fair amount of data, but I don't believe they've published any of that. What I hope to do is publish tagged data sets in future, and those data sets might be more applicable for AI training than simulation data. Thanks again for your attention.